quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. We will watch the universe the way a patient camera watches a landscape, not rushing, not judging, just observing. We begin near our own century, where choices still matter, where stars still shine close enough to feel familiar, where your next breath is a meaningful unit of time. Then the clock stretches. Decades, millennia, eons. We pass the last human-labeled calendars and keep going, guided by physics that stays calm even when the timescales turn unbelievable. Along the way, we will meet the long lives of stars, the fading of galaxies, the quiet math of entropy, the strange patience of black holes, and the far future possibilities that scientists discuss carefully. Some ideas are solid, supported by measurements and well-tested laws. Some are plausible, but not yet fully confirmed. Some are speculative, and we will label them clearly. The tone here will stay gentle and understandable. We will not try to scare you with numbers, even though the numbers will be enormous. We will treat the future like a landscape, wide, slow, and real. This is The End of Time, Timelapse. Chapter 1. The Near Future, the Familiar Sky. The archive begins close to home, because that is where the details are sharpest. Picture Earth at night. City lights form bright patterns, like gentle constellations drawn on the surface of a dark globe. Satellites move like slow fireflies. The moon is a steady companion. The sun rises and sets as if it always will. But even now, the universe is not still. It only looks still when you measure time with a heartbeat. A simple fact to start. Light is fast, but not instant. When you see the sun, you are seeing it as it was a little more than 8 minutes ago. That is the time light needs to cross the space between the sun and Earth. When you see Jupiter in the night sky, you are seeing it as it was tens of minutes ago. When you see Saturn, it can be more than an hour. When you see the bright star Sirius, you are seeing light that left it about 8.5 years ago. When you see the Andromeda galaxy as a faint smudge, you are seeing it as it was about 2.5 million years ago. The sky is a museum of old messages, and the universe keeps sending them. In the near future, the first big changes are not cosmic, they are local. They happen because living things and technology can move faster than stars. The archive notes a familiar pattern. Civilizations build tools, then build questions. They learn to measure. They learn to compare ideas with evidence. They learn to build machines that extend their senses. A telescope is just a time machine with a glass eye, and telescopes are only one part of it. In the next decades and centuries, curious minds will likely keep doing what curiosity does, improving instruments, testing models, and using the universe itself as a laboratory. We already use nature as a physics experiment. A star core is a fusion reactor. A neutron star is a test of matter at extreme density. A black hole is a test of gravity in its most intense form. The cosmic microwave background is a fossil record of the early universe. Here is a calm physics fact that changes how you see everything. The laws of nature do not care about scale. The same conservation rules that apply to a bouncing ball apply to a galaxy. Energy cannot be created or destroyed, only transformed. Momentum is conserved. Electric charge is conserved. These are deep symmetries that show up everywhere. Near future civilizations will keep using those symmetries. Gravity is one of the most reliable rules we have. You can treat gravity as a force pulling things together, or as the shape of space-time, depending on the problem. Either way, it is predictable enough that we can land robots on other worlds, swing spacecraft around planets like slingshots, and aim antennas at distant targets. A fun physics fact that feels like magic. A gravitational slingshot does not create energy out of nothing. It steals a tiny bit of the planet's orbital energy. It is like taking a microscopic sip from a moving river. The spacecraft speeds up, the planet slows down by an amount so small you will not notice, and energy is conserved. In the near future, the archive expects more of these careful tricks. More probes, more mapped asteroids, more experiments in space where the environment is quiet and cold. More observatories listening in many colors of light. Radio, infrared, visible, ultraviolet, X-ray, gamma. And not just light, also gravitational waves, which are ripples in space-time itself. Gravitational waves are a good reminder that the universe has more channels than our eyes. When black holes collide, they can shake space-time. Detectors on Earth can measure that shake as a change in length smaller than a proton, smaller than the size of a single particle. The fact that we can measure that is both absurd and true. The archive also marks another near-future change. The growing ability to measure time itself with extreme precision. Atomic clocks already keep time by counting the vibrations of atoms. Those vibrations are so stable that atomic clocks can notice time running slightly differently at different heights on Earth, because gravity affects time. This is not science fiction. It is general relativity in daily engineering, a calm reality. Time does not flow at exactly the same rate everywhere. In stronger gravity, time ticks slower. When satellites orbit Earth, their clocks need corrections for both their speed and Earth's gravity, or GPS would drift. In the near future, we may measure the universe with clocks as much as with cameras. Now, the archive shifts its lens to the energy sources that power familiar life. We already understand the basics of how stars work. Stars shine because they are giant balls of plasma, held together by gravity with nuclear fusion in their cores. Hydrogen becomes helium, releasing energy, because the helium nucleus has slightly less mass than the 4 protons it came from. The missing mass becomes energy, according to E. Chern's MC2. That equation is famous, but the calm truth behind it is worth saying slowly. Mass and energy are 2 ways to count the same thing. If you convert a little mass, you get a lot of energy, because c, the speed of light, is huge. In the sun, about 600 million tons of hydrogen are fused into helium each second. That sounds impossible until you remember the sun is enormous. It converts about 4 million tons of mass into energy each second. That energy leaves as light and heat. The sun loses mass by shining. Not much on human timescales. But the archive is patient. It will keep watching. It also watches the solar system as a dynamic place, not a frozen diagram. Even now, asteroids move in resonances. Comets visit from the outskirts. Planets tug on each other, and the sun slowly evolves. The solar system is stable in the sense that it does not fall apart quickly, but it is not perfectly still. A teen-friendly way to imagine this. The solar system is like a well-rehearsed dance that still has tiny improvisations. Most steps repeat. A few steps drift over time. One more near-future milestone, the motion of galaxies. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second. That is fast. But they are also very far apart. So the collision is slow. When 2 galaxies collide, Stars usually do not crash into each other. Space is too big. Imagine two swarms of gnats passing through each other. The gnats rarely hit, but the gravity of the swarms reshapes everything. Gas clouds compress, new stars form, and orbits change. This future merger is one of the first big events the archive marks with a timestamp that feels grand, a few billion years from now. But before that, the sun itself is the main clock. It is a reliable, steady clock, like a candle that burns with a consistent flame. Except the candle is a star, and the flame is fusion. Right now, the sun is in a long, stable stage called the main sequence. It has been shining for about 4.6 billion years, and will shine like this for about 5 billion more. That seems like forever. And then the archive zooms out and shows how short that is, because even a long-lived star is brief compared to the deep future. This chapter ends with the sky still bright, still familiar. The night still has many stars. The universe still has many ways to store energy in organized forms. Hot stars, warm planets, chemical gradients, living bodies, and technology. Entropy is present, always. But it is not yet the main character. Not yet. The archive closes this page gently and turns it. Chapter 2. The sun changes, the earth lets go. A time-lapse has a certain kind of honesty. It does not argue, it shows. The archive sets its camera on the sun and lets the years pass. In a few 100 million years, the sun will be slightly brighter than it is now. That is not a guess from mood. It comes from stellar models and the physics of fusion. As hydrogen in the core is used up, the core slowly changes and the balance shifts. The sun brightens by roughly 10% every billion years. 10% sounds small, but climate is sensitive. Earth's habitability depends on a fragile set of balances. How much sunlight arrives? How much is reflected? How much heat is trapped by greenhouse gases? How oceans and rocks exchange carbon dioxide? How life affects the atmosphere? How continents move? How clouds form? Even without asteroids, without wars, without drama, long-term solar brightening is a serious pressure. Over very long times, Earth's oceans are likely to change. More heat means more water vapor in the air. Water vapor is itself a greenhouse gas. A warmer ocean means more evaporation. A warmer atmosphere holds more water vapor. Feedback loops begin to matter. The archive avoids a single dramatic date because the exact timing depends on details. Cloud physics, the carbon cycle, plate tectonics, long-term atmospheric evolution. But the direction is clear. As the sun brightens, Earth becomes less comfortable for complex life as we know it. Maybe life adapts. Maybe technology intervenes. Maybe human descendants move outward, building habitats where conditions can be controlled. Maybe they shade Earth with space mirrors. Maybe they adjust the carbon cycle intentionally, or move the planet slightly outward with repeated gravitational assists using asteroids. These are ideas people have discussed. They are difficult, but they are not forbidden by physics. The archive does not assume success or failure. It simply notes choices, possibilities, and constraints. A simple constraint. You cannot cheat energy conservation. You cannot build something from nothing. You cannot cool a system without sending heat somewhere else. Every solution is an engineering conversation with the second law of thermodynamics. Here is that law in an easy form. In an isolated system, entropy tends to increase. Entropy is often described as disorder, but that can be confusing. A better picture is entropy measures how many microscopic arrangements correspond to the same macroscopic state. When entropy increases, energy spreads out and becomes harder to use for doing work. A hot cup of cocoa in a cold room cools down because there are many more ways for the energy to be spread out into the room than concentrated in the cup. The cocoa does not usually heat itself back up, not because it is impossible in the strict sense, but because it is astronomically unlikely. The universe is the ultimate room. Stars are the cocoa. Now the archive steps forward by billions of years. The sun reaches a future stage. It begins to run low on hydrogen in its core. When core hydrogen is mostly used, the core contracts under gravity and heats up. A shell of hydrogen around the core begins fusing more intensely. The outer layers of the sun expand. The sun becomes a red giant. This is one of those facts that can feel personal, even though it is billions of years away. The sun will not stay like this forever. When the sun becomes a red giant, its radius grows hugely. It will likely engulf Mercury and Venus. Earth is in a complicated zone. It might be engulfed, or it might survive, but be scorched and stripped, depending on details like mass loss from the sun and tidal interactions. Many models suggest Earth is likely to be lost, but there is uncertainty. Either way, Earth as we know it will not remain. During the red giant phase, the sun's outer layers will be cooler, but much larger, so the total luminosity is much higher. If you were watching from far away, the sun would look redder and bigger. Its spectrum shifts because the surface temperature drops, even as its size increases. The archive pauses to add a calm physics note. A star's color tells you its surface temperature. Blue stars are hotter. Red stars are cooler. This is why a red-hot piece of metal is cooler than a white-hot one, and why blue flames are hotter than yellow ones in many cases. Now the archive adds something else. The sun is not just growing, it is also losing mass. As the sun expands, it loses mass through stellar winds. That means the gravitational pull weakens slightly. Planets drift outward as the sun loses mass, because their orbits adjust to conserve angular momentum. This outward drift is real, but it is not a rescue plan. The expanding sun and the changing radiation still make the inner solar system unrecognizable. Then comes helium fusion. When the core gets hot enough, helium can fuse into carbon and oxygen. In stars like the sun, this begins in a dramatic event called the helium flash, because the core is partly supported by quantum pressure, electron degeneracy, and does not expand smoothly at first. The physics is real, but we can summarize it calmly. The sun finds a new fuel for a while, and the balance shifts again. Eventually, the sun runs out of usable fuel for fusion in the center. It cannot fuse carbon into heavier elements efficiently because it is not massive enough. So it sheds its outer layers into space, creating a planetary nebula, a glowing shell of gas. At the center remains the core, a white dwarf. A white dwarf is a star's ember. It is about the size of Earth, but with about half the mass of the sun. That means it is incredibly dense. A teaspoon of white dwarf matter would weigh tons, not because of magic, but because gravity has crushed the atoms so tightly that electrons are packed into a quantum state that resists further compression. Quantum physics is the reason white dwarfs exist. Electrons are not tiny beads that can all sit in the same place. They are waves, and the rules of quantum mechanics prevent them from all occupying the same state. That creates a pressure called electron degeneracy pressure. It is not heat, it is not fusion, it is a quantum rule. So the sun becomes a white dwarf, slowly cooling over trillions of years. the local sky changes. Our solar system becomes a quieter place, with no bright sun, only an old, fading white dwarf, and whatever planets remain, cold and dark, perhaps orbiting in silence. If there are descendants, they might live in habitats powered by fusion reactors, or by extracting energy from remaining gradients, or by starlight from other stars, or by the slow warmth of background radiation while it still exists. Or they may be gone. The archive does not insist, it watches. The archive also watches the galaxy, because the fate of a solar system is not separate from the fate of a galaxy. A few billion years from now, the Milky Way and Andromeda begin their slow gravitational dance in earnest. As the galaxies approach, their dark matter halos overlap first, like invisible clouds of gravity passing through each other. Then their outer stars begin to feel the tug. Long tidal tails form, streams of stars pulled out by gravity. Gas clouds compress. Star formation can increase for a time, especially as gas is driven toward the center. Over time, the two galaxies merge into a new, larger galaxy, sometimes nicknamed Milkdromeda. From inside, the night sky would look crowded. There would be arcs and bands of stars. The familiar Milky Way stripe might be replaced by multiple glowing structures. But this is not a forever party. Gas is not infinite. Star formation uses it up. Some gas is blown out by supernovae. Some falls into black holes. Some becomes locked into long-lived stars or into remnants like white dwarfs. Eventually, even galaxies begin to age. Chapter 2 ends with a double fading. The fading of our sun into a white dwarf, and the slow reshaping of our galaxy into a merged future home. The archive turns the page again. The timescales stretch. The camera pulls back, and the universe begins to look less like a place of bright fires and more like a place of embers. Chapter 3: The Age of Stars and the Last Lights. The archive labels this era with a simple phrase: the stelliferous era, the time when stars still form and shine. We are living in it right now, and it will not last forever. For a very long time, stars will keep shining in some form. But the kinds of stars will change as the universe evolves, and the way galaxies look will change as their fuel runs down. The archive begins with a truth that feels like a riddle. Big stars live fast and die young. Small stars live slow and die old. This is one of the most counterintuitive but beautiful facts in astronomy. A star with more fuel does not necessarily live longer. Massive stars burn fuel much faster because their cores are hotter and denser, and fusion runs at a furious rate. A star with 20 times the sun's mass may live only a few million years. A star with half the sun's mass may live tens of billions of years. A red dwarf with a tenth the sun's mass can live trillions of years. Trillions. That is not a poetic number. It is what the equations and models suggest. Why do small stars last so long? Because the rate of fusion depends very strongly on temperature. In massive stars, the core is so hot that fusion reactions happen extremely quickly. The star is like a powerful engine with its throttle pushed down. In small stars, the core is cooler. Fusion is slower. The star is like a careful candle. Red dwarfs are small, cool, and efficient. Many are fully convective, meaning hot material from the core mixes with cooler material from the outer layers. This mixing allows red dwarfs to use a larger fraction of their hydrogen fuel than stars like the Sun, which have a more layered structure. In the deep future, red dwarfs become the main stable lights of the cosmos. The archive shows the big, bright stars fading out early, leaving behind supernova remnants neutron stars, and black holes. It shows what a supernova really is. Not just an explosion, but a rebalancing of forces. In a massive star, fusion creates an outward pressure. When fusion can no longer keep up, gravity wins and the core collapses. The collapse can rebound and blow the outer layers away, scattering heavy elements into space. Those heavy elements matter because they are the raw materials for planets, chemistry, and life. Carbon in your cells, calcium in your bones, iron in your blood, oxygen in your lungs. Much of it was forged in stars and spread by explosions. So the era of stars is also the era when the universe builds complexity. The archive lingers on the physics of fusion because it is the main engine of this age. In stellar cores, quantum tunneling helps fusion happen. Protons repel each other electrically, but quantum mechanics allows a small chance that they can get close enough for the strong nuclear force to bind them. In the Sun, fusion happens slowly, partly because this tunneling probability is small. That is why the Sun can shine steadily for billions of years, rather than exploding all at once. Another fact, the Sun's fusion starts with the proton-proton chain. In more massive stars, fusion can proceed through the CNO cycle, which uses carbon, nitrogen, and oxygen as catalysts. Same basic outcome. Hydrogen becomes helium, energy is released. The archive moves outward to galaxies. Spiral galaxies like the Milky Way look bright and structured because they still have gas and dust in their disks. That gas forms new stars, especially in spiral arms where density waves compress clouds. Elliptical galaxies tend to be older and redder because they have less gas and fewer new blue stars. Over time, many galaxies become redder and quieter. The bright blue stars die quickly. Longer-lived stars are cooler and redder. Now, the archive steps even farther out. It shows galaxy clusters and the large-scale structure of the universe. Filaments and voids like a cosmic web. This structure grew from tiny density variations in the early universe. Gravity amplified them. Dark matter played a key role, providing the gravitational scaffolding for ordinary matter to fall into. Here is an important cosmology fact said softly. The universe is expanding, and that expansion is accelerating. Distant galaxies are not just moving away through space. Space itself is stretching between them. This does not mean everything is flying apart. Gravity still holds together what is bound. Galaxies, clusters, solar systems, atoms. But on scales larger than gravitationally bound structures, expansion wins. So over immense time, the observable universe from inside a galaxy cluster becomes lonelier. More galaxies slip beyond the cosmic horizon, meaning their light will never reach us because the space between us expands too fast. This is a strange kind of disappearance. Not an explosion, not a crash, but a slow drifting out of contact. The archive makes a gentle point. Horizons are not walls, they are limits of information. Beyond a horizon, events can still happen, but they can no longer influence you. Now the archive highlights a fossil light that matters today, the cosmic microwave background, CMB. Today, it is a faint glow at about 2.7 Kelvin, left over from the time the universe first became transparent to light, about 380,000 years after the Big Bang. It fills space almost uniformly, with tiny temperature variations that encode information about the early universe. As the universe expands, the CMB redshifts to longer wavelengths and lower energies. In the far future, it becomes extremely low energy and extremely hard to detect. So the universe does something subtle. It hides its own origins from late-time observers. An astronomer living in the deep future in an isolated galaxy might see only their local gravitational neighborhood, surrounded by darkness, with no easy evidence of the Big Bang. The expansion would still be real, but the clues would be faint. Knowledge can become harder, not because the rules change, but because the clues drift beyond reach. The archive continues, and it visits some milestone anchors, because time lapses need points to hold on to. Milestone 1, the decline of star formation in most galaxies. This is observed even today. The universe was more active in the past. Star formation peaked billions of years ago and has been declining since. Gas gets used up. Some gas gets heated or blown out. Some gets locked into stars and remnants. Star formation does not stop instantly. It just becomes rarer. Milestone 2, the era where most stars are low-mass red dwarfs. The sky near a red dwarf would be dimmer and redder, but it would last longer. On planets orbiting close enough to be warm, the star might appear large in the sky, and the planet might be tidally locked, with one side facing the star constantly. That creates its own climate challenges, but not necessarily impossible ones. Milestone 3, the last star to form. When will the last star form? Estimates vary. The general picture is that star formation could continue for a very long time in some regions, perhaps up to around 10,014 years, 100 trillion years, or more, depending on how gas is recycled and how conditions evolve. But eventually, gas becomes too thin or too locked away to collapse into new stars. A young viewer might ask, if the universe still has hydrogen, why can it not just form stars forever? The answer is partly about density and cooling. To form a star, gas must collapse under gravity. But gas needs to lose energy to collapse, often by radiating it away. In the far future, gas may be too diffuse, too separated by expansion, or too heated by background processes. Also, a lot of matter ends up locked in remnants and compact objects. The universe's useful gas supply dwindles. At some point, star formation becomes so rare that you can treat it as over, even if a few last events happen in isolated pockets. Now we enter the time of remnants. White dwarfs, neutron stars, black holes, and cold planets. White dwarfs cool. Neutron stars cool. Planets drift. But not everything is perfectly static. Gravity keeps working. Orbits can change slowly through encounters. Objects can collide. Binary systems can exchange energy and rearrange. The archive explains a key idea. Gravitational systems can relax. In a cluster of stars, close encounters can fling some stars outward and send others inward. Over enormous times, clusters can dissolve. This is called dynamical relaxation. The timescale can be long, but the archive has time. There is also another subtle energy leak, gravitational radiation. If two massive objects orbit each other, they can emit gravitational waves and spiral inward, like the black hole mergers we detect today. In the far future, compact binaries could still merge occasionally, releasing bursts of energy. So even in a dim universe, there can be rare fireworks. Now the archive introduces a concept that becomes more important later, the difference between temperature and heat. Temperature measures average energy per particle. Heat is energy in transit due to temperature difference. In the far future, temperatures can be low, but energy can still be present in forms that are hard to use. A black hole can store enormous mass energy, but extracting it is not trivial. As stars die out, the universe's free energy, the energy available to do work, decreases. This is connected to entropy. The archive is calm about it. It does not call it doom. It calls it a trend. Then we reach a far milestone, when red dwarfs, the last long-lived stars, begin to die. A red dwarf does not die like a massive star. It does not explode as a supernova. It gradually exhausts its hydrogen. Depending on its mass and details, it may slowly turn into a helium white dwarf. The transition is quiet compared to a supernova, but it is still an ending of a light. Because red dwarfs can live trillions of years, this moment is incredibly far away, around 10^13 years, 10 trillion years, or more for many of them, and up to about 10^14 years for the smallest. The last steady starlight fades. The night sky becomes truly dark, except for faint glows from cooling remnants and occasional events. The archive camera is still running. The time-lapse does not end when the stars do. It shifts to a deeper kind of quiet. Chapter 4. The Degenerate Era and the Question of Decay. The archive names this next long stretch the Degenerate Era, a time dominated by degenerate remnants, objects supported by quantum rules rather than fusion, white dwarfs, neutron stars, and increasingly, the mass trapped in black holes. In this era, the most common, luminous objects are not stars but remnants that cool slowly. A white dwarf, for a while, might glow faintly in infrared. Over enough time, it cools toward the background temperature of the universe. But the background temperature is also changing. As the universe expands, background radiation redshifts and cools. In the far future, the universe becomes colder than any natural environment we can imagine today. Yet even cold things can change if you wait long enough. The archive pauses here to be careful, because this is where the line between known and possible starts to matter in a serious way. We have strong reasons to think some particles are stable, or at least extremely long-lived. The electron appears stable. The photon is stable. Neutrinos are extremely long-lived as far as we can tell. But as far as we can tell has limits, because we have only watched for a short time on cosmic scales. There is a famous idea from certain grand unified theories. Protons might decay. Proton decay has never been observed. Experiments have set lower limits on the proton lifetime. If protons decay, they do so with a half-life longer than about 10^34 years. Exact limits depend on the decay mode and experiment. That is a number so large that it breaks normal imagination. It is not something you wait for. It is something you only talk about with math. Because proton decay is unobserved, it remains a possibility, not a fact. So the archive makes two parallel notes, like a careful documentary. If protons do not decay, then many structures can persist for extremely long times, limited by other processes. If protons do decay, then ordinary matter slowly dissolves into lighter particles and radiation over unimaginable times. Let us walk both paths gently. Path 1. Suppose protons are stable. In that case, white dwarfs can last an extremely long time. They cool, and their interiors can crystallize. This is not a metaphor. In a cooling white dwarf, the carbon and oxygen nuclei can settle into a crystal lattice, and the star can become, in a sense, a giant crystal sphere. Astronomers have evidence that some white dwarfs begin crystallizing even today, because crystallization releases latent heat and changes how the star cools. So the degenerate era includes a quiet transformation, stars becoming crystals. Over longer times, gravitational interactions can cause encounters between remnants. A white dwarf could collide with another white dwarf or be perturbed into a close orbit. and in rare cases, it might ignite fusion, again through compression, producing a type Ia supernova even in a far future universe. These would be rare, but in a long enough timeline, rare is not never. Neutron stars can also collide, producing bursts of gravitational waves and heavy element production. Today we have observed kilonova events that create elements like gold and platinum. In the far future, similar collisions could happen occasionally, but their frequency declines as structures thin out. Now, path 2. Suppose protons do decay, then a white dwarf is not forever. Its nuclei are made of protons and neutrons. If protons decay, nuclei break apart. The star slowly loses mass and becomes a cloud of radiation and lighter particles. Over times like 10^37 to 10^40 years, depending on details, much of ordinary matter would be gone. This is not a fast destruction. It is a slow whisper. In a time lapse, it looks like a statue turning to dust one grain at a time. If protons decay, you can imagine matter leaking into radiation. Not as heat in the usual sense, but as the steady appearance of energetic particles that then redshift away as the universe expands. What would the universe be made of then? Mostly photons, neutrinos, electrons and positrons, perhaps some stable light particles, perhaps dark matter if it is stable, and black holes if they remain. Neutrinos become especially important in deep time because they interact so weakly. They can carry energy away and rarely bump into anything. The universe can become filled with particles that pass through everything. Now the archive introduces another careful question. What about dark matter? We know dark matter exists because of gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Clusters lens light. The cosmic microwave background patterns fit models with dark matter, and large-scale structure growth matches it. But we do not know what dark matter is made of. It might be a stable particle. It might be something that decays. It might interact with itself. It might be multiple species. It might not. So in the archive, dark matter is a background character. It shapes structure early on, but in the deep future, it becomes a question mark. If it is stable, it remains. If it decays, it adds to the background radiation. The archive does not invent answers. It marks uncertainties. Meanwhile, the universe keeps expanding. Bound structures become isolated. Many gravitational systems slowly evaporate. Objects are ejected by encounters, leaving behind fewer and fewer bound orbits. Over enough time, most matter ends up either in compact remnants or in black holes. And then the archive focuses on black holes, because they are the deepest reservoirs. Black holes are regions where gravity is so strong that not even light can escape once it crosses the event horizon. They are also, in a strange way, simple objects. In general relativity, an isolated black hole can be described by a small set of properties: mass, spin, and electric charge. Charge usually neutralizes quickly, so most astrophysical black holes are described mainly by mass and spin. Black holes seem like perfect storage. Put mass in, keep it forever. But quantum physics adds a quiet twist. Stephen Hawking showed that black holes are not entirely black. Due to quantum effects near the horizon, black holes can emit radiation. This is called Hawking radiation. It means black holes can slowly lose mass and evaporate. The smaller the black hole, the faster it evaporates. For stellar mass black holes, the evaporation time is enormous, about 10^67 years for a black hole with the mass of the Sun, using standard estimates. For supermassive black holes, It can be around 10 to 9 to 10 100 years or more, depending on mass. These numbers are so large that they dwarf the age of the universe today, which is about 1.4 to 10 years. The archive is comfortable with huge numbers. It treats them like scenery. It also adds a teen-friendly explanation of why evaporation happens at all, without pretending it is simple. In quantum field theory, empty space is not perfectly empty. It has fluctuations. Near a horizon, the definition of particle depends on the observer. The result is that, from far away, the black hole appears to emit a faint thermal spectrum. The emitted radiation carries energy away. That energy comes from the black hole's mass. So the black hole loses mass. This does not mean black holes leak like a punctured balloon in a normal way. It means the boundary between quantum physics and gravity produces a slow, steady glow. In the degenerate era, the archive keeps watching as energy sources fade. White dwarfs cool, neutron stars cool. If protons decay, matter dissolves. If protons do not decay, matter remains, but becomes colder and harder to reorganize. The biggest remaining engines become black holes. Entropy increases, energy spreads out, and the ability to do work continues to fade. This is the deep approach to the next milestone, the black hole era. Chapter 5. The black hole era. The long fading. The archive is now so far from our century that names like year and calendar feel like ancient carvings. But physics still speaks the same language. The black hole era begins when black holes are the dominant remaining massive objects, and everything else is cold, faint, and mostly inert. Star formation is long over. Most stars are remnants. Many remnants are gone or decayed, depending on whether proton decay is real. Galaxies have relaxed and thinned. Clusters have become isolated islands. Black holes remain because they are stubborn. The archive camera settles on a supermassive black hole at the center of what was once a galaxy. In our time, such black holes can have millions or billions of solar masses. In the far future, they may have grown by merging with other black holes and swallowing matter during earlier active eras. Then they settle as their surroundings empty. The scene is quiet, but it is not static. The black hole slowly emits Hawking radiation. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A more massive black hole is colder. A smaller black hole is hotter. This produces an unintuitive reality. The biggest black holes are the coldest objects. If you think of them as thermal emitters, they can be colder than the background for a very long time. For a long stretch, the universe around a black hole might still be warmer than the black hole's Hawking temperature. In that case, the black hole absorbs more radiation than it emits. Evaporation is not the net direction yet, but as the universe expands and cools, there comes a time when the background becomes colder than the black hole, and evaporation becomes the net direction. This is an important detail. Black hole evaporation is not only a property of the black hole, it also depends on the environment. Eventually, in the deep future, the environment is extremely cold. Black holes begin to lose mass overall. The archive records that the evaporation is unbelievably slow at first. Then it gets faster as the black hole shrinks. The final stages, if the theory holds, could be dramatic. As the black hole becomes smaller, its temperature rises and it emits more energetically. The last moments might be a burst of high-energy particles, but the archive remains honest. Hawking radiation is a strong theoretical result, supported by deep principles, But direct observation for astrophysical black holes is beyond current technology because the effect is tiny for massive holes. There are analog experiments that mimic parts of the phenomenon, and the theory fits with quantum field theory in curved spacetime. But the archive still uses careful words. Now the archive widens the view and explains why this era matters for the story of ending. Black holes are the last large compact reservoirs of free energy. They hold mass energy in a concentrated form. As they evaporate, that mass energy is converted to radiation. But the radiation does not stay useful. As the universe expands, the wavelength of light stretches with it. This process is redshift. Stretching the wavelength lowers the energy of each photon, because photon energy is inversely proportional to wavelength, so expansion cools radiation. The archive shows the universe as a place where energy is continuously being spread out in two ways. Locally, by processes like emission and scattering, globally, by the stretching of space. During the black hole era, what is happening is mostly the steady conversion of mass into radiation, and the steady stretching that makes that radiation lose energy. Now the archive points to a milestone that feels like a final candle going out, the evaporation of the last black hole. If you follow standard estimates, the largest black holes could take around 10, 100 years or more to evaporate. That is a 1 with 100 zeros. In the time-lapse, this is the slowest fade in the entire story. The archive offers a way to hold such numbers without panic. Think of it like this. The age of the universe today is about 10 billion years. The time for a supermassive black hole to evaporate could be so much larger that if you wrote the age of the universe as a single grain of sand, the black hole lifetime might be like the weight of a mountain in grains of sand. Even that is not perfect, but it is closer to the feeling. The scale difference is enormous. During this era, the universe becomes more and more dominated by low-energy photons, and other light particles spread thinly across vast space. Entropy increases, energy spreads out, free energy fades. Now the archive reaches a crossroads of possibilities, because cosmology matters. In one widely supported future, the universe continues expanding forever, and the temperature approaches absolute zero, but never reaches it. Entropy increases, free energy fades, and the universe approaches a state called heat death, maximum entropy for its constraints, a near equilibrium where no significant work can be extracted because there are no large gradients. This is often described as the universe ending in cold darkness. The archive adds nuance. Heat death does not mean everything is hot. It means everything is at nearly the same temperature. It means the universe is thermodynamically boring. A universe at heat death is quiet, not because it is frozen, but because it is even. Now the archive explains what makes the expansion accelerate today: dark energy. We observe that the expansion is accelerating through multiple lines of evidence, including supernova distances and the patterns in the cosmic microwave background and large-scale structure. The simplest model is a cosmological constant, a constant energy density of space itself. But we do not fully understand dark energy. It could be a cosmological constant. It could be a field that changes slowly over time. It could be something else. Current observations favor something close to constant. That makes the long-term picture more stable. Continued acceleration, continued isolation of gravitationally bound regions, continued redshifting of radiation. But the archive remains careful. Alternative outcomes exist in theory, but are not strongly supported by evidence right now. For example, If dark energy were to grow stronger with time in a particular way, it could lead to a big rip where expansion eventually overcomes even bound structures. This is a known class of models, but current data does not strongly favor it. If dark energy were to weaken or change sign, expansion could slow, or in some models the universe could recollapse. This is also possible in some theories, but again, not favored by current evidence. The archive does not promise drama. It keeps its tone grounded. It then adds one more speculative possibility, clearly labeled speculative: vacuum decay. In quantum field theory, the vacuum is not nothing. It is the lowest energy state of fields. It can have properties. It is possible, in some theories, that the vacuum we live in is not the true lowest energy state, but a metastable one, like a ball resting in a shallow valley that is not the deepest valley. If that were true, a rare quantum event could cause a transition to a lower energy vacuum state. This would propagate at near the speed of light, changing the effective laws of physics locally in a way that would be catastrophic for structures like atoms. This is a startling concept, but it is not a prediction with a scheduled date. It is a possibility discussed in certain frameworks, with probabilities that are extremely uncertain. Some calculations suggest our vacuum might be stable for times far longer than the age of the universe. Some suggest metastability, but with lifetimes far beyond any practical timescale. And practical is a funny word when you are talking about 10 and under 100 years. The archive includes vacuum decay only as a flagged possibility, not as a promised ending. It also notes a comforting point. If vacuum decay happens, we would not see it coming. It would arrive at light speed with no warning. There is no anxiety worth carrying about it. It is either not happening, or it is happening in a way no one can prepare for. The archive does not dwell. It returns to the more grounded story. Black holes evaporate, radiation thins, expansion stretches everything, and the universe approaches an evenness that feels like silence. And then the last black hole evaporates. The universe enters a new phase. There are no more large, compact reservoirs of mass that can slowly leak energy in interesting ways. Only the thin soup remains. The archive turns to its final chapter. Chapter 6. The thin soup, the long quiet. Now we are in what some call the dark era, a universe with no stars, no black holes, no bright engines. Just a vast, expanding space filled with extremely low energy particles, and perhaps stable dark matter drifting through. The archive does not show darkness as fear. It shows it as stillness. There is a difference. To understand this era, it helps to revisit entropy one more time, gently. Entropy is not a villain. It is a count of possibilities. When entropy is high, energy is spread out. Spread out energy is hard to turn into organized motion, into life, into computation, into anything that looks like something happening. In our era, the universe has lots of gradients, hot stars and cold space, dense planets and thin atmosphere, chemical differences between places, gravitational potential. Those gradients are opportunities to do work. In the far future, gradients fade. That is the core of heat death. If you could float in this far future universe, what would you see? Not much with eyes like ours, because eyes need photons of certain energies, and those photons would be rare. The background radiation would be extremely long wavelength, perhaps larger than the size of galaxies. It would not interact with matter the way visible light does. It would be more like a gentle, nearly uniform hum, a faint sea of waves stretched thin. If there are particles, they are sparse. The mean distance between them can be enormous. Interactions become rare. Time still passes, but it has fewer events to mark it. Now the archive addresses a deep question that teenagers often ask in their own words. Does the universe end, or does it just keep going? Physics, as we know it, does not require time to stop. It allows the universe to keep expanding and cooling indefinitely. In that case, the story does not have a dramatic final scene. It becomes quieter and quieter. But the archive also acknowledges the mind's need for honest possibilities. There are still small possibilities for change, even in deep quiet. For example, if protons are stable, then matter can persist. Over immense times, even stable matter can undergo changes through quantum tunneling. Quantum tunneling allows particles to pass through energy barriers with a tiny probability. In everyday life, that probability is so small that it is effectively zero. But effectively zero is not the same as zero. Given times like 10⁻50 years, 10⁻100 years and beyond, processes that are negligible today might become relevant. Some physicists have discussed whether matter could reorganize through rare fluctuations, whether new structures could form, whether strange, observer-like fluctuations could occur in a thermal background. These ideas are deeply speculative and controversial because they depend on assumptions about cosmology, entropy, and the nature of time and observers. The archive includes them only as footnotes in the margin, not as central narrative. It does not want to mislead. The main line remains: the universe trends toward equilibrium. Another possibility is that dark energy changes, but current evidence suggests it is close to constant. Another possibility is vacuum decay, flagged earlier, but its probability is unknown and may be irrelevant for any timescale we can meaningfully discuss. So the archive returns to the most scientifically grounded picture: a slow fade to a cold, dilute, near equilibrium universe. In that universe, the phrase "end of time" does not mean a sudden stop. It means the end of meaningful clocks, the end of frequent events that create new complexity, the end of easy stories. A clock is any repeating process: the rotation of a planet, the ticking of a pendulum, the vibration of an atom, the pulsing of a star. In a universe that is nearly empty and nearly uniform, there are fewer repeating processes and fewer interactions to mark a rhythm. Time might still exist as a dimension, but the universe stops giving you convenient handles to measure it. That is one definition of an ending. Not that the page is torn, but that the ink no longer changes. The archive spends a long moment on one last, quiet physics fact. Even in the far future, the laws of physics do not become emotional. They do not become cruel. They remain consistent. They are the same rules that let a soap bubble form, that let a rainbow appear, that let electrons make chemical bonds, that let your brain store memories. The same rules that allow sunsets also allow heat death. That is not a betrayal. It is a unity. The archive then does what an archive does. It records without panic. It imagines the last structures fading, the last bound orbits disrupted, the last particles decaying if they do, the last radiation stretching to wavelengths so long that old words feel too small. Space expands. The background cools. Entropy reaches near its maximum, and the universe becomes a calm, thin soup. If there is any comfort, it is this: endings in physics are often asymptotes. They are approached, not slammed into. The universe does not need a dramatic finale. It can simply become quieter forever. The time-lapse slows, frames stretch, the archive light dims, the camera is still, because there is almost nothing left to track. And finally, the archive closes. Not because the universe ends, but because the story has reached its quietest stable form. This was a quiet archive story, where the story ends, sleep begins,